Everybody to this third video in my animating in Desmos series. Hope that you guys have found the other two videos useful, and in this video hoping to show you how to make your animations a little bit more interactive. In terms of thinking about this video, it's a little bit more video gamey than my other two in the fact that you can manipulate things and then have that animation deal with whatever initial settings were given by your students. It's super cool. If you are interested in jumping to a certain part of the movie, I have been putting the chapters and the time breaks down below in the description, so you can check that out, so that way you can skip to the part that you find most beneficial. Definitely, I think this is kind of like the hidden vegetables of math, the fact that this is how you kind of get students to buy in a little bit, and there is a lot going on behind the scenes, but once students connect with the situation and they can get their hands in it, just students really buy in, and they start to love the things that you're doing if they see connections to outside of just the classroom discussion. So a couple things to maybe think about. First, if we are jumping, we are following a parabolic path up and down. And in this video, I'm planning on jumping over a boulder. And so you go up over the boulder and back down and land on the ground. So when we're designing this, we have to kind of think about the math behind that. So we're going to be following a quadratic, and we're going to have to wrestle a quadratic out of some points that are pretty vague. They can be in lots of different places and situations all at once. So we're going to have a starting point and a stopping point, and that will kind of be set in stone. And then the last thing is we're going to have a third point that is adjustable, and you can move it basically anywhere you want. So how do we wrestle a quadratic out of those 3 points? And in the middle of this tutorial, I'm actually going to take a break and make a separate video so you can see how the math connects to everything that is going on here. And it's kind of interesting, but if you're not a mathy person like myself, then that's something you don't have to necessarily watch. So let's go ahead and let's get going in the graphing calculator. I'm going to start by making a background folder. So you can just type in folder. And I always like to do this because it's easy. But we're going to bring in the image that kind of sets our scene. And when I was making sure that all the pieces fit and creating that resource for you guys to use, I thought that this scene was a little bit too dark. Sometimes it's hard to see images on top of other images. And so I'm going to go ahead and knock the opacity down to 0.65. That makes it a little bit lighter, a little bit more transparent. And if you've been watching my other videos, you know that I like to set my scene at 20. So it's 10 in each direction, -10 to +10. Vertically and horizontally. And that's basically it for the background. So we'll go down here, we'll create another folder, and this is going to be my mathy stuff folder. So in my mathy stuff folder, I'm going to have to create these 3 different points that students can scooch around and interact with. And so the first point is going to be called Z1 because it is on the x-axis. It's actually called a 0, or you could say it's a root. If you're in Algebra 2, those should be vocab terms that you're familiar with. And so this is going to be x sub 1 and then 0. Okay, it's going to be stuck on the x-axis. And so we can take this point and we can slide it. Oh no, we can slide it everywhere right now. What I would like to do is I'm going to change this so that it is slidable only in the horizontal directions. And so that's one of these options that you can do off to the left-hand side. So now you'll notice when I drag it, it is stuck on the x-axis, which is great. We're going to go ahead and we're going to create a second point, the second 0, and that is going to be x2, oops, and 0 as well. And I'm going to add that slider in, change the settings so that it's draggable only horizontally, and so now I have these 2 points. In order to make this maybe a little bit more intuitive, I'll make the first point green, so like that's where you start, and then the second 0 is where you land, so that'll be red. Now, only 2 points at the moment. I need to go ahead and create a third point, and I'm just going to call this x3, y3, and this is going to be somewhere in the middle of those 2. And for colors, I'll make it orange, kind of like you're slowing down. So I have green to orange to red. Now, one thing I'm kind of noticing as I look at the scene is that the picture itself isn't really centered. So the ground isn't at the same height as these zeros, which is kind of what I intended. So I'll come up to the background folder, And I'll change the height of, hey, that worked out. The background needs to be at 0, 2 instead of at 0, 0. So you can see these draggable points are now on the platform. So we'll minimize that folder back up, and we'll come back into our mathy stuff folder. Now this next part is going to be a little bit of an aside. One of the hardest things about making and creating your own activities in Desmos is trying to think like a kid who's going to intentionally break things. And you have to find the bugs in your own designs, and you have to try to squash those things so that kids can't screw up, your intention. And I've already designed this in an older activity, but this was kind of my second chance to view it and clean things up. And one thing that I really wanted to do was make sure that these points stay in the same order, that they don't get flip-flopped or you don't move certain points out of the way. Because when we create our function, sometimes it will disappear if it's not set up, in green to orange to red in that order. So one thing that we're going to have to do, Desmos unfortunately allows you to drag points anywhere, okay? And so some kids might drag their point outside of the window of the activity. So this first 0, the x1, needs to have a boundary on the left-hand side. So underneath that, I'm going to create what's called a left bound, and that needs to be at -10. Oops. And what you can do to make Desmos absolutely never go past -10 is you can lock that in. So it gives you the inequality, the compound inequality, and we're just going to say from -10 to -10, and that is non-negotiable. So back up here in x1, I want the leftmost value that it can go to be the left bound that I just defined. And so it will never go past -10. Before, I was dragging this over to the -11, -12 range, and now it can't, okay? If you look at red can go that far. I'm going to have to deal with that here in a little bit. So left bound is as far left as that starting point will go. It can go off the right-hand side of my window, and that's not good. We'll deal with that here in a minute. So the second 0 needs to not be allowed to ever go out the right-hand side. Since I'm going to try to keep them in this order, the right-hand part of the window is kind of out of bounds. So we're going to make a right bound and do something similar, but that is going to be 10, and we'll lock it in at 10 to 10. That way you will never be able to slide this point out outside of this amount. Oh, yeah, so right now you can kind of see, even though I said right bound, it still can go outside because I haven't actually told the point to only go to the right bound. Almost screwed up there. So now these points are kind of confined to our window of our game, if you will. The point that's kind of critical is actually the center point. Right now, if I really wanted to be facetious, I could switch green and red and make the character jump backwards, which is not good, okay? So I need to keep the green point to the left of the orange point, and I need to keep the red point to the right of the orange point, and then allow a little bit of cushion room. So what's going to probably happen is back up here in Z1, the right-hand side of how far that first point can go needs to be x3. x3 is that center orange point, but I'm going to buffer it by subtracting a little bit. So right now, if I go to the orange point, you can see I'm stuck. There's an invisible force field there that I cannot get past that orange point. If I move the orange point, now I can get a little bit further. But this prevents me from getting the points out of order. I'm going to do the same thing with the red point, except it's going to be x3 and then adding a little bit. So that way I can never stack the points entirely on top of each other. That would be bad. Yeesh, talk about not being a function. So now I can't go further left than the orange point, and I can't go further right than the window here that I'm allowed. But some interesting things kind of happen if you move the orange point around. You can potentially scoot those zeros out of the window entirely, and that would not be good because then students would lose those points. If we're going to try to keep this orange point from causing some serious problems, we're going to have to limit where that orange point can live. And so down below x3 and y3, we're going to create a center left bound. I've already used left bound for the green point and right bound for the red point. So these are the center left and the center right bounds. And so that center left bound, if I make it -10, I still actually have the potential of scooching that point outside of the window, which would be bad. So I need to factor in that buffer that I had above and say -9.9, and I want to lock this in, just like the other numbers that I'm doing, so that Desmos can't wiggle around it. So the leftmost value of x is going to be center left bound. Okay. Then we're going to go ahead and we're going to make center right bound. And we're going to lock that in at 9.9 as well. And we have to go back up to the x value since this is left and right and make that our rightmost value. It's hard to type and talk at the same time sometimes. The other thing that's going to be an issue is if I take that orange point, and students will do this, they'll find a way, is they will throw it out of the window vertically. Okay, and they'll say, Mr. Johnson, I can't do my problem because the orange point isn't there. I jumped too high. Which, as we'll see here in a minute, the path you might take could go out of the window, but that point should always be locked inside what we can see. And so we're going to make a center up bound and a center down bound. And the center up bound, remember I moved the whole image up 2 units. That's going to be 12. And I want to lock it at 12. And then a center down bound. That's hard to say. And that is at -8, because it's 2 units up from the typical -10 that I do. And that's locked in. So if we come back up to the y values, the heights, we need to go from the center down bound to the center up bound. All right, and that should be good in terms of not being able to scooch my points out of the window itself. So hopefully you kind of followed that. That just takes experience, and it takes sometimes giving your class an activity and seeing what happens. I always write down notes about like, this didn't work, students did this, fix that bug. And it's just part of life. So now that we have our 3 points, we're going to have to wrestle that quadratic out of here. It's a quadratic that is wiggly all over the place, just dependent on where these 3 points are. And I have some math that goes behind this, and the other video will really explain kind of how this works, because you can look it up on the internet, but it doesn't necessarily explain how you get from the beginning to the end. In my case is a special case because I have the starting point and the ending point as x-intercepts, as zeros. So the thing that you'll find probably on the internet won't look exactly like what I'm going to write. But we need a jump path that is a quadratic, and so I'm just going to type this as jump of x, and that is equal to, if you watch the other video, the third y value multiplied by x minus x1 multiplied by x minus x2, which if you kind of see structure, those are the 2 0 values, but I'm going to divide this whole thing by x3 minus x1 and x3 minus x2. And you can see it doing all sorts of crazy things, but by the end it settles itself down into a quadratic, which is just so awesome that we have this path. And the cool thing about this is you can move these points kind of wherever you want, and the quadratic will adjust accordingly, which is so cool that you can change your jump flight. The one thing that I kind of like, because I'm OCD about the visuals here, is I'm going to make this black and dashed, and maybe change the weight of the line so it's not as thick. The other thing that I don't like is when you jump, you are not going to jump through the ground. So continuing this quadratic down into the negative territory is probably not realistic. And so I'm going to chop this up with a domain restriction. I'm going to say it needs to be graphed from x1 less than or equal to x less than or equal to x2, since that is the second 0. And there you go. From green through orange to red at your stop. Now, one thing to note, I did find that if you do not include the equal to part of that compound inequality, your images here, when we connect the character to this graph, might disappear. So because time starts at 0 and you are literally on that green point, if you can't equal that green value, your image won't show up. It'll be invisible. And then as soon as time starts, it'll show up and start jumping. And that's why you have to include the equal to. And it's a small little thing that if you're not thinking about it, it can cause you big frustrations. So let me expand this a little bit. And now we have to get to the point that actually travels from green to red. So down below the jump function, I'm going to go ahead and create a point that is called the center, because I will hook it up to the center of the image. And that is equal to, at the moment, x1, and then jump of x1. I'll change this point to maybe purple. Not that it really matters. It'll be turned off eventually. But you can see the purple point is right on top of the green point. And I believe we should be able to drag that point. It's not letting me for whatever reason. So one thing that we're going to be using here in a second is time. And if you've watched the other videos, time is critical for animating things. And so I usually start time at 0, and it goes from 0 to 20. And then I go ahead and play that back at 1/5 speed, because that makes it real time. Don't worry about if our animation goes too long, because we'll chop it off in the CL layer. The other thing that's nice to be able to control is the speed of the animation, because time will flow at 1 unit per second. Like it just cannot go any other way. But if you want your animation to go a little bit faster, you're going to have to change the speed at which it cycles through. So speed. And I, for whatever reason lately, have just been making speed go 0 to 10 and step by ones. Not that you have to do it that way, and we'll set the speed to be 7, I've kind of found, is you want this to be a faster animation because you're jumping. You don't just float in the air. We aren't Michael Jordan or Olympic long jumper here. Although we are jumping over a boulder, which is pretty impressive. So now I have to go ahead and take these things and factor them into the center point. So I'm going to go ahead and add in my speed times time. And then I need to take that as well and plop it into the y value, or the x value of the function. And I hate there's not space between there because it's hard to read. So let me change and start time here. And you can see that it didn't take very long for that purple point to hop up and over. And the fact that it disappeared is kind of like in prior videos when your animation would just fly outside of the window. We will deal with that. But it would be nice to know how long that takes, because depending on the speed, you can change this all over the place. That amount of time that you need to let the animation go for will change according to the speed. The faster you go, the shorter the amount of animation. The slower you go, the longer that you'll need. And so it would be great to know the end time. So I'm going to make a variable for that. And that end time is based on where I start and stop, like how far do I need to go. So that would be x2 minus x1. And I have to divide that by how fast I'm traveling. So I need to divide that by speed. And if I do that, Desmos will output that it takes about 1 second for me to finish. So right now I'm at 1.2 seconds. If I change this to 1.1 second, which is really close to the end time, you can see that purple dot showed up at the end. So this is a great estimate. This is the accurate amount of time versus my slider just goes in tenths of a second. Now that we know some of those variables and we have our path all figured out, I'm going to start a new folder for my character. So this is the actual image that is going to be jumping instead of that purple dot. So I'll go ahead and drag him in. His image is a little bit off center, so we'll have to kind of deal with that in a second. He's also huge. So I'm going to go ahead and create a size slider. Typing, my arch enemy. We meet again. So now that I've set the width and the height to be size, because it was set at 1, it was pretty small. So I'm going to move him over to the center by just backspacing the static point of 0, 0, the origin, and typing center, or whatever you name that point. And you can see it gets instantly hooked up to that purple point, which I forgot to turn off. Okay. So now that we have that, he is also standing kind of below that point because it's the center of the image. So one thing that we can do, I know I have center, and center is referring back to that initial point, but we can break that point back up if you put parentheses around it and say center dot x and then center dot y. It takes the x value of center and it takes the y value of center. And basically this is the same center point, but now that I've ripped it apart, I can add, 2, or I can add, 1.9 to it. And so you can fiddle around with that. If you think about all the different possibilities, like if I change his height, adding 1.9 doesn't cut it anymore. And so really what you should be adding to the y value is his size, but divide that by 2. It's half of his size. Ooh, and his shoes are floating on the ground there a little bit, so I might want to divide by slightly more than 2, just because of how I drew my image. It wasn't perfectly centered. So, all right, good for us. You also notice he's standing kind of behind the green point, so we'll want to do the same thing with the x value. So maybe I will add the size, but divide that by 5.5 or something like that. Okay, so his feet are a little bit more right on that green point. He's still huge, so let me go ahead and I will resize him. And notice how, he kind of stays centered and locked in at that green point. If I hadn't have done it in terms of size, I would have to go back and change those amounts. So we'll make him so he can fit through one of these doors. That's a good scale. So we have the size, we have the center, we have the width. And if I go ahead and take my time slider, and I usually like to keep my time slider out of my folders because it's what I do to test to see the animation, we can see that he literally jumps up and jumps down, and it takes about a second for him to travel from A to B. Don't worry that he disappears. We'll fix that. So after we have all those things kind of figured out for a character, it's time to bring in the boulder. So we're going to make another folder. We're going to call this the Boulda Folda, which rhymes. Good for us. Need to bring in my image. Drew a nice, lovely boulder here. A little bit of Indiana Jones action. And the size, I'm just going to change it so it's not as big. 7 by 7. Seems reasonable to jump over a 7-foot boulder. And the center actually is going to be hooked to another point that we're going to define here in a second. So let me make this the boulder center. And that boulder center maybe starts at 12, so off outside of the screen. And I'm just going to make it 12, 0 and kind of see how that looks. Notice my boulder did not move. It's because my boulder is not actually hooked up to the boulder center yet. And it would be nice to actually have that boulder center up a couple units. So let me try like 1.8. I still want a good chunk of it to be like over the ground, so that way it looks like it's continually rolling on the ground and not like floating up there. Okay, so it's good that a little bit of the boulder is poking into the window. That way kids can see it. They see our character and they are told in the instructions to move the points. And so I'm just going to leave this at the moment. I would like it to stop, the boulder to stop at the origin or at 0,2 or whatever. So if you're recalling from the other videos, I know I have overall time. That's for the animation of the jump. But I'm going to need a second source of time that actually is connected to the boulder. My thought on this was having students launch the boulder and then having a separate button that will launch them into their jump. So there are two components to kind of control, which means that there are two types of time. So I'm going to make boulder time, and that's going to power my boulder animation. I'm going to start boulder time at 0, just like the others, 0 to 20, and I'm going to make that play back at 1/5 speed. Okay, in addition to boulder time, I'm going to need boulder speed. And that is going to control how fast that boulder rolls into the scene. So let me set it at, I don't know, 4 or 3. And we're going to go from 0 to 10. Oops, not 100. Step by ones. So I have my boulder speed, my boulder time, and my boulder center. And so this boulder center needs to start at 12 and go leftwards, which means I'm subtracting the speed multiplied by the time. And I don't need to actually copy this to the y value because the height of the boulder is just going to stay at 1.8. So let me play boulder time and see how that works. Looks good. Oh! Whew. We almost got smashed by that boulder. So now that I have the boulder animated to its own time, I need to know how long it's going to take before I need to stop time, similar to how I need to know how long it takes to jump before I stop the jump time. So I'm going to say boulder end time. And that is going to be determined on where I started, which is at 12. Put this in parentheses. And where I'm stopping, which is at the origin. I have that in my head that I want it to stop right in the center. And I'm going to divide that by boulder time. And so it takes me almost 3.1 seconds. So if I slide back here, yeah. Oops, it's not divided by boulder time. Excuse me, it's divided by boulder speed. Whew. Yeah, I wondered why the answer changed there for a second. So it's the speed at which we are traveling. Because that didn't look like it was right at the center either. Okay, so it's sliders. Great stuff. So it takes me about 3 seconds to go from 12 to here, which makes sense if you're traveling at a speed of 4 times faster. The only other thing that I didn't like, so this boulder just slid right in, which is not how boulders do their bouldering stuff. Okay, we need to be rocking and rolling. And so in order to do that, we're going to actually come back up here and change the angle. So I'm just going to go into that box. And the angle that we're going to be needing is based on boulder time. And boulder speed, I think. Okay, so it's based on where it's at that certain time. You can already see it's changed. If I play this, I mean, that might be it. It seems a little fast. Kind of like it's just turning too fast. It wouldn't work like that because certain sides of the boulder have to be stuck on the ground almost. So I'm going to take that and I'm going to divide it by pi because I think it's based on rotation. And now it seems a little bit too... it's not quite there. So it needs to spin maybe a smidge faster than that. So I don't know. It just takes a little bit of guesswork. I probably could look this up. But that seems reasonable. So you're always wanting the bottom of the boulder to kind of stay static on the ground. And then as it moves, the edge of the boulder is kind of gobbling up new units in the graph, if you will. So now that I have all that done, we're going to go ahead and clean this up and make it look a little bit prettier. So depending on your situation, you might want the grid and the axes completely turned off. I'm going to go ahead and make everything step by ones because I might ask my kids some questions just about the logic of the situation. Where did you start? Where did you end? And to make it maybe a little bit more relevant, I'm going to talk about the x value in terms of distance and doing it in feet versus height, again in feet. And don't be too worried that distance and height are off the screen here. When you put it into the activity builder, they will be smushed inside the window that we define. But this looks pretty nice. The only other thing that I try to do is I try to scramble everything up for students so that way they aren't given the answer right away. So I put the green point somewhere where it probably won't end up. I put the orange point. Obviously, you don't want to jump down. And then the red point is not far enough. If the boulder stops in the middle, that red point's going to need to be over here, and the orange point will need to be positive. But this kind of just sets the scene for them to start somewhere where they have to think critically about what they were given. So let me save that. Probably want to title that something that you can find it later. And we're going to copy this link and then go over to the activity builder. So creating a new activity here. We'll call it boulder jump or whatever you want. And then on this screen, we're going to go ahead and have a note. We will need a graph. There it is. And I'm going to make this all vertical. You'll see kind of how that looks. And then I need 2 buttons. One for the jump and one for the boulder. And so it squishes it all vertically. I think that looks nice here. We'll title it So the note itself is mainly just for instructions. So I have something pre-written students can read to kind of understand what they're supposed to be doing. If the boulder will roll to the point 0, 2 before stopping, can you position the jump path of the character to clear the obstacle? Hint, you can move all the points that are visible. When you're done, test out your hypothesis by clicking the button to launch the boulder and then click the second button to jump over it. So those are the 2 different actions that I have. So actually, since I copied and pasted that, I have to come back here and get my link. We're going to go into the graph, just paste that URL into the graphing calculator, and it should import all of this for us, just how we left it, which is perfect. We will come into the CL layer here in a minute, but before I do that, I'm going to go ahead and label my buttons. So launch the boulder is that first button, and then jump is the second button. So the CL layer, most of the coding is going to go into the graphing component. So we're going to need to talk about the bounds. And remember, we need to make the bounds static here in this situation. And it goes -10 to the left, it goes 10 to the right. But because we shifted the whole thing up early on in the video, it only goes down to -8 and then up to +12. If you don't do that, you might get a little white strip at the bottom if you just make it 10s all the way. The second thing that we're going to need to do is we're going to need to import or create a number, and the CL layer pushes this number into the graph to make the animation go. And so that number is time. Notice I'm putting the subscript all in curly brackets to keep I, M, and E, those characters, together. Otherwise, they just float around and get lost, and there's an error and all sorts of bad stuff. And so the time is going to be based on when you push the jump button, okay? So when, I need to title those buttons. So this is going to be boulder button. And this is going to be jump button. So I put the boulder button first because that's the first thing that they'll be pressing. I know I'm coding the jump button. So when jump button dot time since press. So when they press this button for the first time, what do I want this button to do? Well, first off, I need this to actually be the amount of time since they pressed it up to that certain point. At some point, I want it to cut off and just stop and shut down. So whenever this is less than this dot number, and I need to go into this component, into the graph, and look for the number end time. So when I am less than the end time, what do I want this to be doing? Well, I want it to do the jump button dot time since press. Okay? So when I press it right away at like 0.1 seconds, it's going to check, is this less than the end time that I specified? Yeah, it's not end time yet. Okay, so just keep on going. 1 second, is it less than the end time? Yes, keep on going. But when, oops, took apart my parentheses. When I get to the other side of like, now I'm at 3 seconds, is 3 seconds less than the end time? Uh-oh, no, 3 seconds is way over. I need to have this otherwise condition that is going to put the end time as the only thing to look at. It will be essentially stuck at end time. When you're less than end time itself, time will flow, and when you're over end time, it's going to be stuck at this value that I'm coding. So I'm going to put this dot number and then end time. So essentially this only allows your time to flow up into that point that we determined back in the graph. We'll see how that works here in a second, but I need to be able to do the boulder time as well. And I'm going to do the boulder time in a similar way since I'm cutting that off. So number, boulder time. And notice I'm using the syntax where everything's in that orange slant quote. So that is kind of math type for Desmos here. And so we'll do the same thing when boulder button dot time since press is less than. Oh, I wonder if I was supposed to have an equal to. Okay, so less than or equal to this dot number, and then this was boulder end time. What do I want it to do if it's less than boulder end time? Well, I want it to do boulder button dot time since press. Otherwise, if I start to pass that end time, I want it to be this dot number and then boulder end time. Now there may be some issues in my test run. I actually had to subtract a little bit from end time to get the image to show up, but we're going to try this and we're going to see if that less than or equal to addition there kind of fixed the issue. So let's preview this. We can see I need to adjust my points. Okay, the instructions up there, if you read those, let's launch the boulder. Comes running in, jump! All right, he jumped, which was great, and you can still kind of, ooh, he appears here. Interesting. So I need to, because he disappeared, I think I need to go ahead and go back into the CL layer and adjust this a little bit. So it gets stuck at end time, which depending on how Desmos thinks about things, sometimes it can be a little bit more accurate than what the timer is. So to fix this, I just subtracted a smidge, just a pinch off the end. So like subtracting, oopsie, you notice it gave me an error there, subtracting 0.001. If you are within those orange slant tick marks, it is going to be able to do math for that. So I took the end time, I just subtracted a little bit so that it's stuck inside of the preview window. So when we launch the boulder, oops. And this is nice that, you know, it's not going to crush you to death right away. We can jump, and it's stuck there because it's just a little bit before that end time amount. So he's visible at the beginning, and he's visible at the end. And for some reason, the first time that I tried to code all this stuff, that was really frustrating to me. I'll have to look into why it's still kind of disappearing at the end. That'll be something interesting that I can try to problem solve. But hopefully you guys enjoyed this video. I really enjoy making these, and I hope that they're helpful to you and that you get something out of those. If you haven't watched my first two videos, I'd encourage you guys do that. You could subscribe. I'll hopefully make a few more of these in the future, and you can get updated on that. The other video on the math wrestling out that quadratic that we did in the middle should be up at some point. It's a little dry, but it has a lot of good stuff in there for honors Algebra 2 students, some factoring, some quadratics, and systems and things like that. It's pretty fun. It was fun to solve if you like a good problem to think about. I was really wanting to do this quadratic example because if you can take this and go backwards to lines should be super easy. And so I would encourage you guys, maybe explore that, try it on your own. You're more than welcome to take my resources and change them and manipulate them to kind of fit whatever you're hoping to do in your classrooms. But I appreciate it. If you guys have questions or want to leave any comments or things like that below the video, I would love to talk nerdy math, Desmos stuff with you guys. And I hope that you take care, and we'll see you in the next video. Peace out, guys.